If we were to play a game show, one of the easiest questions would be, how long does it take for the Earth to revolve around the Sun? The answer is about 365 days. You knew that, I'm sure. But the million-dollar question would be something closer to, how long does it take the Sun to revolve around the center of the Milky Way galaxy? Care to guess? Is it closer to 200 hours, 200,000 days, 200 million years, or 200 billion centuries? Keep reading to find out what the answer is and why it matters in helping us figure out the mass of the Milky Way galaxy. Before we dive in, I want to set a little more familiar example for you so you can understand what I'm blabbing about later on in this lesson about how astronomers figure out all this stuff. Our solar system can be used as a parallel to our galaxy. The center of our galaxy is like our sun, and the planets orbiting around our sun are like stars in our galaxy orbiting around the center of the galaxy. Simple enough. Okay. Our sun is massive. In our solar system, almost all of the mass is therefore concentrated in the sun. Because of this, something known as Keplerian motion occurs. Keplerian motion is a fancy term for orbital motion which follows Kepler's laws of planetary motion. What does that look like and actually mean? Well, because our solar system's mass is concentrated in the sun, the orbital velocities of the planets decrease as you increase the planet's distance from the sun. Put another way, relative to Earth, the orbital velocity of Mercury is faster. Conversely, the orbital velocity of Neptune is much slower because Neptune is so far away from the sun. Therefore, we can predict that if essentially all the mass of the galaxy is concentrated near its center, the orbital velocities would decrease as you moved away from its center. Keeping that in mind, let's see how we find the mass of the Milky Way. Stars in the disk of the galaxy, like our sun, will basically follow a circular orbit within the plane of the disk. Scientists have calculated that our sun moves around the center of the Milky Way at a speed of approximately 240 kilometers per second. Since it's hard to imagine what that speed is like, I like to put such numbers into perspective. That's like a round-trip voyage from New York to Paris in less than a minute. Because we strongly believe that the sun's orbit is almost circular, we can use this notion, the estimate of the distance from the sun to the center of the Milky Way, which is 8,200 parsecs, as well as basic geometry to find the circumference of the sun's orbit. By dividing the circumference, 2 times pi times r, of the sun's orbit by its orbital velocity, we find that the orbital period of the sun is about 210 million years or so. This is known as the galactic year, the time it takes for the sun to revolve around the center of the Milky Way galaxy. Now you know the answer to the million-dollar question. So, the next question is, why does this number, 210 million, matter in finding out the true mass of our galaxy? Well, binary systems, two celestial objects orbiting around a common center of mass, reveal their total mass, mass A plus mass B, when you cube the average distance between the stars, A, in astronomical units, and divide that by the square of their orbital period, P, in years. We already know P. It's 210 million years. We also know that each parsec equals 2.06 times 10 to the fifth astronomical units. By multiplying the latter number by 8,200 parsecs, we find out that the radius of our sun's orbit is equal to about 1.69 times 10 to the ninth astronomical units. By plugging and chugging, that means the mass of our galaxy comes out to be 110 billion solar masses. But that number is a gross underestimation because it includes only the mass lying within the orbit of our sun. Scientists estimate the mass of the galaxy to be at least 400 billion solar masses and is likely to be much higher, over 1 trillion solar masses. And here's why. If you've already forgotten my solar system example, tying it into the galaxy, recall what I said before. We can predict that if essentially all the mass of the galaxy is concentrated near its center, the orbital velocities would decrease as you moved away from the center. But through observation, we know the opposite occurs in our galaxy. The orbital velocities in our galaxy's disk are either constant or increase with distance away from the center. What does this mean to you? Think about it for a second. It must be that the galaxy has a lot more mass than what's found within the orbit of our sun. This extra mass is found in the galactic corona. The galactic corona is a low-density and low-luminosity spherical distribution of matter surrounding a galaxy that extends great distances beyond the edge of a galaxy's visible disk. The majority of this matter is invisible. It is dark matter, or matter that neither emits nor absorbs light, and is detected solely by its gravitational influence, and it makes up the majority of our galaxy's mass. In fact, it makes up 90% of the matter in our galaxy. This means that only 10% of the galaxy's mass is in the form of visible objects, like our stars. This mysterious invisible dark matter, which gives our galaxy such significant mass, is the subject of another lesson. Keplerian motion, orbital motion which follows Kepler's laws of planetary motion, predicts that if essentially all the mass of the galaxy is concentrated near its center, the orbital velocities of stars would decrease as you moved away from the center of the galaxy. Observational evidence has shown that the opposite is true. Orbital velocities either stay constant or increase at a larger radius. By using the galactic year, the time it takes for the sun to revolve around the center of the Milky Way galaxy, as well as several other figures, we find out that the estimate of our galaxy of 110 billion solar masses is a woefully lowball number. That's because such calculations exclude mass outside the radius of our sun's orbit. The real mass of the galaxy is at least 400 billion solar masses. This extra mass is found in the galactic corona, a low-density and low-luminosity spherical distribution of matter surrounding a galaxy that extends great distances beyond the edge of a galaxy's visible disk. The majority of this matter is invisible. It is dark matter, or matter that neither emits nor absorbs light and is detected solely by its gravitational influence.